Math 1314, Tyler Junior College, Section 3.6, Polynomial and Rational Inequalities. Polynomials from graphs to inequalities. In this final section in Chapter 3, we're going to transition from equations and functions to inequalities. So far in this chapter, we have studied polynomial functions, starting with quadratic functions. And we've studied rational functions, functions that were ratios of polynomials, whose graphs frequently have vertical asymptotes, horizontal asymptotes, and under certain conditions, slant asymptotes. But what does this have to do with solving inequalities? Now, we've solved inequalities already in a previous series of videos. I believe that would be Chapter 1, Section 7, when we solved both linear inequalities and absolute value inequalities. But why bring them up now? Well, there's a strong relationship between some inequalities and the graphs of some functions. Specifically, if we have a function involved in an inequality compared to 0, so a function greater than 0, a function less than 0, a function greater than or equal to 0, or a function less than or equal to 0, then there's a natural representation of the solution to any of these inequalities on the graph of the corresponding function. On the board, I have a graph of a generic polynomial function, which we're calling f of x. And just to make sure we're clear on what we're implying here, the graph starts out the left end rising, if you will, comes down and crosses the x-axis at x equals a, whatever number you want to put here, dips down to a minimum, and then curves back up and crosses the x-axis again at b, continues to increase until it hits a maximum, and then it comes back down to an x-intercept of c. However, this time it doesn't cross the x-axis, it touches and turns around, at which point it proceeds to go up and hits a maximum, comes back down, crosses the x-axis one final time, and then the right end continues to fall for the rest of the graph. As an interesting challenge, it would be neat to see if you could put together a function whose graph would do this generically. The intercepts are easy to build. Just remember the factor theorem. Every intercept is a 0, which is a factor. One of these intercepts would have an even multiplicity. Do you know which one it is? And to make sure the end behavior did what it was supposed to, you might have to adjust the leading coefficient a little bit. But I invite you to see if you can build. You know what? I'm talking about it. Let's go ahead and do it. What I'm about to do is not actually part of what's over there, but since I brought it up, at the end of the videos for series 3.4, we talked about rebuilding functions based off of zeros. If you have a 0 like a, then it corresponds to a factor of x minus a. That's the factor theorem, or part of the factor theorem. And since we have 4 x-intercepts, we should have 4 factors: x minus a, x minus b, x minus c, x minus d. However, multiplicities dictate that an odd multiplicity will cause the graph to cross the x-axis, whereas an even multiplicity will cause the graph to touch the x-axis and turn around. Since c is the only x-intercept where the graph touches and turns around, then the corresponding factor should invoke an even multiplicity. Recall that multiplicities come from the powers, so this factor would need an even power. 2 will suffice. But this isn't quite good enough, because if we were to check the end behavior of this using the leading coefficient test, the leading term would be x to the 5th power. Think about it. 5 factors, each start with an x. And if you analyze the end behavior for a leading term of x to the 5th, it would be left falls and right rises. In order to reverse that, we would have to stick a negative in front of it. So like I said, it's an interesting challenge to attempt to write a function that's associated with a graph of given characteristics, but with enough practice, it's not nearly as hard as it seems. But I digress. What does this have to do with polynomial inequalities? Well, in order to answer that, let's answer these 3 questions, the first of which we've already answered. What are the zeros of f of x? Recall that zeros are values that make a function equal to 0, and relative to a graph and a function, the input is the x and the output is the y. So if you put all that together, the zeros correspond to where y is equal to 0, which is precisely where the x-intercepts are. So the zeros of this function are exactly at a, b, c, and d. But let's talk about the intervals where this function is greater than 0, in other words, positive. This is equivalent to asking where is the output positive, or where is the y-coordinate positive? Well, if a point's y-coordinate is positive, that means that it went up above the x-axis. So asking the intervals on which this function is greater than 0 is equivalent to asking on what intervals is this graph above the x-axis. Well, it starts out above the x-axis back at negative infinity until it hits a. But once it hits a, it's no longer above the x-axis until it hits b. Between b and c, it's above the x-axis, so the interval from b to c. And similarly, the interval from c to d is above the x-axis. Now you may have noticed I've used parentheses on these, and in this case it's out of necessity. Because if I put a bracket on them, it includes the endpoints. The endpoints are zeros of the function, which make f of x equal 0, but I'm saying strictly greater than here. So had this been that, greater than or equal to, then I would have had to put a bracket on everything except the negative infinity. In fact, had it said greater than or equal to 0, these two intervals would have actually joined together because they both end and start at c and c is included. It would have just been bracket b to d. But I don't want to overanalyze this. The point that I'm making is visually a function is positive when its graph is above the x-axis. So naturally a function is negative when its graph is below the x-axis. Do you see the interval or intervals on which this function is negative? It's clearly below the x-axis between a and b, so we can say that interval. But where else is it below the x-axis? Did you catch this piece over here? It's below the x-axis starting at d and continuing forever. So is this what I'm going to ask you to do, or is this what I'm going to teach in the next series of videos? Not really, but this is going to motivate what's about to happen. So let's think about what just happened. If we are attempting to solve a polynomial inequality, it's visually equivalent to saying where's the graph above or below the x-axis. But in order to find those places, we have to find the values that separate where the graph is above the x-axis from where the graph is below the x-axis. Those points that separate are precisely the points that are on the x-axis, aka the x-intercepts, aka the zeros of the function. So our strategy in solving these polynomial inequalities will start by finding its zeros. In other words, pretending it says equal and then solving that. Once we find the zeros, we'll be able to partition the number line into intervals. In this case, negative infinity to a to b, b to c, c to d, d to infinity. Then the task will boil down to figuring out on which intervals the function is positive and which interval the function is negative. That's actually pretty easy. Because if it's positive on an entire interval, then it's positive for any given number in between. So to test whether a function is positive or negative on one of these intervals, we simply have to test it at a single value. In the next video, we'll refine this concept and apply it to an example or two. It's actually pretty straightforward and I think fairly intuitive.